So let's think a little bit about nuclear energy. This sort of picture you have seen in your GCSE textbooks, I'm sure, explaining how a nuclear power station works. The way I think of it, a nuclear power station is really a little bit like a kettle. You have to generate steam, and that steam drives turbines, which drives motors, which generate electricity. The question is, how do I get the heat to develop the steam? I could burn coal, I could burn gas, or I could use nuclear fission. And that is how a nuclear power station works. So you've seen this sort of diagram, but what I thought we could do is do something a little bit more dramatic than that sort of cold schematic diagram. So if you just cast your eyes onto the screen, onto the left-hand side, you'll see what a nuclear power station really looks like. And we're actually going to show you some of the components here. And in fact, we're actually going to operate this power station. So let me hand over to my beautiful assistant, Bob. Okay, so that shows a sort of cutaway of a real nuclear power station. Now, I need to tell you about some of the components of this nuclear power station and a little bit more detail than you probably need to know for your GCSE. So we're going to zoom in on some of the components. The first component I want to zoom in into is the fuel. So let's have a look at the fuel. So there you can see the top of the core and you can see the fuel rods within there. We can actually, I think, show a photograph of the fuel rods. There they are. Well, nuclear power stations actually have different sorts of fuel rods, and we've got some examples here. You'll be pleased to know there's actually no nuclear fuel in these, otherwise I wouldn't be able to pick them up. But this is a fuel rod from one of the early nuclear power stations in the UK, the old Magnox power stations. There's only one of them still operating in the UK at the moment. You can see it's a fairly large fuel rod there. Most of our power is actually provided by advanced gas-cooled reactors in this country. And this is a fuel rod from an advanced gas-cooled reactor. You can see it's much smaller than the Magnox one. This is made of stainless steel, a similar sort of stainless steel that your cutlery is made of. And the reason for that is it doesn't corrode so badly. And then a modern-day nuclear power station, a pressurized water reactor, which is what you're looking at there, contains fuel rods like this. This is a rather exotic material made of zirconium alloy. It's called zircaloy 4. Actually, this is an interesting fuel material because this was the problem with the Fukushima nuclear power station. Because if you heat this material up too hot, it actually generates heat itself. And that's where a lot of the problems came from. This corroding at very high rates, at very high temperatures, generating hydrogen, which actually led to the explosions you saw. So we're looking to develop new, safer fuel materials, and we're doing research here to do that. So that's the fuel. So let's zoom back out again. So the next component I want to tell you about is the reactor pressure vessel. This is one of the largest components in the nuclear power station. There you can see one. You can just about see the size of people alongside that. We can't make these in this country. They're just too big. They actually get made in Japan and in France. And in fact, the next power station we're going to build in this country, the reactor pressure vessel, which looks just like this one, has already been ordered and already been made in Japan. Now, that reactor pressure vessel is made of steel. It's made of ferritic steel, which is a sort of steel that is magnetic. And this little specimen is a bit of that sort of steel. But it's a little bit more complicated than that, because on the outside is the magnetic ferritic steel, but actually on the inside surface, we put stainless steel on to stop it corroding as well. So that's the reactor pressure vessel. And then the last component I wanted to show you was the pump. So you can see these are pretty big components. You've probably seen little pumps in your home. Well, this is the size of one of the pumps in a reactor pressure vessel. It's a very large component, and this is also made of stainless steel, again, because we don't want it to corrode, we want it to last for a long time. These power stations are going to be built to last for at least 60 years. In fact, there's talk in the US about some of these reactors operating for 80 years or even 100 years. So can you imagine a century worth of electricity from one nuclear power station? Okay, so we've shown you some components, and we can show you some more if you're interested a little bit later, but I thought it would be quite fun to actually try and operate this power station. I'll just show you some of the mechanics of what you do. So Bob's going to be our reactor operator for this, and then I might ask for a volunteer to have a go themselves. So the first thing we have to do is we have to start the nuclear reaction occurring, and the reason it stops is because we have control rods into the core. So we're going to raise the control rods out of the core. So up they come, and what you can see now is the core temperature starting to increase, because now the nuclear fission processes are occurring and the core is getting hot. So now what we need to do is to start pumping water through the core, not only to cool it and control the temperature, but to take that hot water to a steam generator that's going to generate steam just as a kettle would. So let's start the pumps. Okay, so now the water is pumping through. The temperature of the water is round about 350 degrees centigrade in a pressurized water reactor. So it's quite easy for that very, very hot pressurized water that's not boiling to pass that heat through actually tubes just like this to colder water on the outside to boil the water, which is what happens in the steam generator. So then we need to take that steam out to the turbines, which is the third control, and that is when we'll start generating electricity as the turbines start to spin. And you can see at the top right-hand side that we're now generating 1,710 megawatts, 1.6, 1.7 gigawatts of electricity, and we're matching the demand. So now our reactor is operating safely, and it's stable, and we're generating electricity. So now we'll just shut it down safely, and I just wanted to ask if there's anyone who would like to have a go at operating this reactor. You can pop your hands up. Look at this. Okay, well, one of you, in fact, the one that's second in from the right, slightly closer to the right-hand side, do you want to come out and Bob will show you? Yep. Bob will show you how to operate a nuclear power station. Okay, so the first thing we need to do is to lift the control rods up out of the core. Now, of course, if there's an accident or something happens that we need to shut the reactor down very quickly, those control rods automatically drop down into the core.
Core temperature near maximum.
Okay, so you need to get the pumps going. Start cooling the temperature of the core. Okay. And then we'll start the turbines going. Okay, so you are now generating 2.2 gigawatts of electricity. So you're really driving this quite hard. Okay, so let's shut it down safely.
Demand matched. Well done.
Okay, let's give him a round of applause. Okay, so let's just look in a little bit more detail about the materials that I touched on that make up a nuclear power station, and we'll shut this down safely and everyone will be happy. Can we cut the sound? Thank you. Good. Okay, well, this game, actually, we're going to develop this so this can come out into schools and it can help you learn about nuclear power, about the components and everything like that. And ultimately, we want to put it on the web so that anyone can have a go and play with it and learn something about nuclear power. So Bob wrote that program, so perhaps give him a round of applause as well. Okay, let me tell you a little bit about materials in nuclear power stations. So I said the reactor pressure vessel is made of ferritic steel. That's the steel that's magnetic. If you look at that steel under a microscope, at fairly high magnification, that is what you'll see. That's called the microstructure of that material. And what you find is that different materials have different microstructures. So the pipework is made of stainless steel, and you can see there's a difference in how that looks like under a microscope. And the turbines, the blades within the turbines are made of a nickel-based alloy, and again, the microstructure looks different. So the composition of all those materials are different, and they look different under the microscope. And it's that link between the microstructure and the properties that you want for your material that is absolutely critical when you choose what materials you're going to use for which components. So let me show you 4 things that really influence how materials perform: their microstructure, the stress and the strain that you put on those materials, the environment in which they operate, and also how quickly or slowly things happen. So when you fire a bullet at steel, things happen very quickly. But if you built a cannon 400 years ago and you left it to rust, things are happening slowly. So the rate at which things happen affects the performance as well. So let me just illustrate that. Let's look at the microstructure first of all. And this is an experiment that we undertook at the university here. So here we've got a little steel rod which is quite strong, and you can see the microstructure down there. The microstructure makes it very strong, makes it very hard to deform the material. But if we heat that material up, we actually change the microstructure within that. So now it's heated to red hot. If we then put that into very cold water, we quench it, and that changes the microstructure, and it changes the properties. So all of a sudden, that steel that was very strong becomes brittle, and you can actually snap it like a twig. So the microstructure is very, very important. Secondly, stress and strain, the loads that you apply to structures, is very important. Now, this is a test flight, and I want you to watch the back of the aircraft. Okay, so if you put a high stress on something, be it an aircraft or whatever, things will happen. The performance of those components will not be as you want them to be. But it's not just the external loads we apply. Actually, materials have got stressors inside them. So these 2 brass tubes, the one on the right has got an internal stress. It's called a hoop stress, and it runs around the circumference of that cylinder. This is put into mercury chloride. And if you watch the one on the right, you can start to see cracks forming and growing up the length of the cylinder. And it's the stress there that's driving those cracks. The one on the left was stress relieved. So stress and strain has an important influence on the way components behave. And we'll come back to that a little bit later. Thirdly, the environment that you put your component in has an effect. Here's some mild steel that's been put in concentrated nitric acid. And you can see it's passive, nothing's happening. Now we're going to change the potential, the electrochemical potential of the environment, and get the oxide off the steel. All of a sudden you find that the steel corrodes uncontrollably. So the environment in which you operate a component has a huge effect on its performance. And actually, corrosion is one of the biggest challenges for all structures. The last example is rate, how quickly or slowly things happen. And this is a really important aspect for nuclear power stations. Here you can see some weights on some wire, some lead wire. And you can see slowly the wire gets longer and longer and longer and longer. And that process is actually called creep. Eventually, things break due to that very slow deformation process. And you'll see the one on the left break in a minute. And that's one of the factors that limits the lives of nuclear power stations, and something that we try and control. There we go. Okay, so the materials that we choose for our power stations is incredibly important. So again, what are the key factors? Well, nuclear power stations are made from all sorts of materials. There's other ones I haven't even started to tell you about. And each one is selected for its microstructure and its properties so that the whole power station operates safely all together, each component playing its part. And the performance of all of those components is dependent on the material, is dependent on the stress and strain, is dependent on the environment, and it's dependent on time. So again, if we think back to the Fukushima nuclear accident, certainly the components were put under a lot of stress and strain due to the earthquake, but actually they were designed to withstand that, and they did. The problem was that the environment combined with the materials led to this high exothermic reaction where heat was generated by the fuel cladding, the zirconium fuel cladding, and that's what led to the problems. And that occurred pretty quickly, so time was an important factor.